Good morning, my YouTube viewers. Crystal here. In this video, what we're going to do is we're going to discuss the nonparametric runs test. So the runs test is also called a Wald Wolfowitz runs test. It checks whether a sequence of observations is random. It is one of the simplest and most interpretable tests of randomness because it looks only at the order of values and not their magnitudes. So a null hypothesis is the sequence is random, so that's independent observations. And an alternate hypothesis is the sequence is not random, so too few or too many runs. So in order to demonstrate the runs test, what we're going to do is we're going to go over the code of a runs test. So the first thing you want to do is you want to set your seed. The reason why you set your seed is so every time you run the program, the variables are going to initialize to the same values, and that way the program runs the same every time. So you type set.seed brackets 1, 2, 3, and you can put any number that you want within the brackets. And then we're going to create some example data, which is a numeric sequence. So X is a randomly distributed normal distribution. A randomly sampled normal distribution at 40 samples. And then we're going to convert it to a binary sequence, which is above or below the median. So med becomes the median of X. And then so sequence bin is if else. If X is greater than or equal to med, it's 1, otherwise it's 0. So we're going to count the number of positives and negatives. So N1 becomes sum brackets seq bin equals 1, and N0 becomes sum brackets seq bin equals 0. So N is the length of seq bin, and I'm going to take it that it's going to be 40 in this exercise, and the reason why I'm going to take it that it's going to be 40 in this exercise is because you have 40 samples, and so I'm going to take it that it's going to be 40. So we're going to count the runs. So run becomes 1 plus brackets seq bin negative 1 does not equal seq bin negative n. And then expected runs and variance under randomness, mu, which is your mean, becomes brackets 2 times n1 times n0 divided by n plus 1, and sigma 2, which I'm going to take that to be the standard deviation, becomes brackets 2 times n1 times n0 times brackets 2 times n1 times n0 minus n brackets divided by n squared times n minus 1. And then so sigma, which that's going to be your standard deviation. So sigma 2 is going to be like your variance, and sigma is going to be your standard deviation because with the variance, you get a formula for variance, and then the standard deviation is the square root of variance. So sigma becomes square root bracket sigma 2. So I don't know why they didn't put variance in this program. I don't know why they called it sigma 2 because it's a little bit confusing. But you've got your variance, and the standard deviation is actually the square root of the variance. So now we're going to calculate the z statistics. Z becomes brackets runs minus mu, which is your mean, divided by sigma, which is your standard deviation. And that's your Z. And then we're going to calculate a two-tailed p-value. So p-value becomes 2 times p norm, and p norm is a probability distribution of the normal distribution, brackets negative ABS Z. So that's the negative absolute value of Z. And then we're going to print the results. So you have list, runs equals runs, expected runs equals mu, Z equals Z, and p-value equals p-value. So now we're going to plot the sequence with runs highlighted. So plot brackets SEQ bin, comma, type equals S, comma, line width equals 2, comma, color equals steel blue, comma, main, which is your title, is runs test visualization. XLab, which is the label on the x-axis, is index. YLab, which is the label on the y-axis, is binary value above or below median. YLim, which is the limitations on the y-axis, is a vector going from negative 0.2 to 1.2. And then we're going to add run boundaries. For I in 1 to n minus 1, if brackets SEQ bin I does not equal SEQ bin I plus 1, then AB line brackets B equals I plus 0.5, comma, color equals tomato, comma, LTY, that it equals 2. So that means it's a dashed line. And then we're going to put the legend in the chart. So legend brackets top right, comma, your legend is a vector, a binary sequence, and run boundary. Color is a vector of steel blue and tomato. And line width is a vector of 2. So the binary sequence is 2 and the run boundary is 1. LTY is a vector with the binary sequence being a straight line and the run boundary being dashed, and BTI equals N. So we run the program. So you had 17 runs and you had 21 expected runs. Your Z value was negative 1.28 and your P value is 0.2. So if we were using it as a hypothesis test, then we would fail to reject the null hypothesis. So we've got our runs test visualization where we have visualized the runs test. And then so you've got the index, which is 0 to 40. And the reason why the index is 0 to 40 is because you had a randomly sampled normal distribution of 40 samples. So this is taking, giving you what every sample looks like from 1 to 40. And then you've got your binary variable, whether it's above or below the median. So if it's below the median, it's going to be 0. And if it's above the median, it's going to be 1. So that's telling you whether every every sample is above or below the median. And then you have the run boundary as well. So that's how you do the runs test. And the next video, we're going to be talking about some more statistical subjects. So I hope you decide to watch the next video, and I hope that you get something out of this video. And thank you for watching.